Hello everyone, myself Dr.P.Vijayakumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In this session, we are going to see the continuous random variables. One of the application is Gaussian random variable. So at the end of this particular session, so the learning outcome 1 is understand the Gaussian random variable concept and its applications, and the learning outcome 2 is apply the Gaussian random variable concepts for solving the real-time problems. So firstly, we will recall what is meant by Gaussian random variable. A Gaussian random variable is a type of continuous random variable which follows a normal distribution, one of the most commonly used distribution in probability and statistics. And this normal distribution was first introduced by De Moivre in 1733, who derived it as a limiting form of the binomial distribution. The result was later extended by Laplace and others, but it has been attributed to Gauss, who first published a reference to it in 1809. So, normal distribution was famously known as Gaussian distribution function. So, Gaussian distribution function is mainly used in many applications. One of the familiar applications is communication systems. So, for noise modeling, there we use Gaussian distribution function. Thermal noise in the receiver is modeled as additive white Gaussian noise. And also for performance analysis, for bit error rate calculation using digital modulation schemes like BPSK, QPSK and QAM, and in the channel modeling, the fading is generally assumed as following a Gaussian function for estimation of errors. And similarly, we use in signal processing also. So, for random signals and generation of random signals follows the Gaussian function, and for errors also follows the Gaussian function. And also this is also used in filtering applications. Kalman and Whelan filter assumes the Gaussian noise as the default noise while doing the filtering operations. And also in estimation theory, for calculation of MMSE and ML estimations often relies on Gaussian concepts only. So, and also when it comes to electronics and hardware also, thermal noise generation follows the Gaussian function. And also for process variations in VLSI fabrication also, we use this Gaussian random variable. And A to D converters, D to A converters, the quantization noise is often approximated as a Gaussian random variable. So, nowadays in machine learning also we are using Gaussian random variable for future distribution modeling, and Gaussian random variable is also used as naive Bayes classifier, classification applications, Gaussian mixer model, regularization and noise injection during training. So, there are many more applications. We have listed few applications here. Okay. So, firstly we will see what is meant by a Gaussian random variable. A random variable is said to be a Gaussian random variable if it has the following density function. The density function is fx of x is equal to 1 by root 2 pi sigma x square e power minus of x minus mu x whole square by 2 sigma x square. So, we know that here sigma x square is the variance of the variable, random variable, mu x is the mean of the random variable. So, this is the Gaussian density curve. It is a bell-shaped curve and the maximum value is located at mean value. So, when x is equal to mu x, the maximum value f max is equal to 1 by root 2 pi sigma x square. Okay, this is the maximum value we will get. And when you integrate this one, we know that the distribution function is the integration of density function. When you integrate the Gaussian density function, the curve will be approximated curve will be like this. So, we cannot directly do the integration for a Gaussian function. Instead, we use some special functions for calculation of integration for distribution function. So, here that is what I mentioned here. Direct calculation is not possible. Instead, what we do is we will convert the given Gaussian random variable into a normalized Gaussian random variable just by simply replacing x with x minus mu x by sigma x, where sigma x is the square root of variance and it is nothing but standard deviation, mu x is the mean. So, we will replace x value with x minus mu x by sigma x. Then the newly formed function is the normalized distribution, Gaussian distribution function. So now we will compute this with the help of special functions. So phi of x minus mu x by sigma x, because of that the function is reduced, which is close to a q function. Now the new function will be very much close to a special function. With the help of this special function, we calculate the integration or we calculate the distribution function values. The special function here we are using is q function. Q function is mathematically defined as 1 by root 2 pi some integration x to infinity e power minus y square by 2 into dy. Okay, if x minus mu x by sigma x is replaced with x, Gaussian density function is 1 by root 2 pi sigma x square e power minus x square by 2. This will be the newly formed Gaussian function. Now you can see this Gaussian function is pretty much close to this function. Then distribution function is the integration of density function. Now you can see this Gaussian function and q function are similar except for the limits. Here the limits are minus infinity to x, here the limits are x to infinity. So the relationship between q function and Gaussian function is f of x is equal to 1 minus q of x. For example, if you want to compute f of 5, 1 minus q of 5, like that we will calculate. And the q function can be calculated based on the table or using the approximation formula. Q function q of minus x also can be written as 1 minus q of x. So for a q function there is an approximation function, either we can use the approximation function or we can use the table. Q function table is available. So based on the table we can calculate. So the direct integration is not possible. We are using the special functions for computing the distribution function here. Let us see one problem. How do we compute and how do we apply the Gaussian random variable concept for real-time problems? Let us take one real-time problem. For example, the current in a diode is following a normal distribution and the mean value of the current is 10 milliampere, variance is 4 milliampere. Mean value is mu x is equal to 10 milliampere, variance sigma x square is 4 milliampere. What is the probability that the measurement will exceed 12 amperes? That means the probability of x exceeds 12 milliampere. So the probability of x greater than 12 can be written as 1 minus probability of x less than or equal to 12. Here what we are doing? We are replacing x with x minus mu x. Mu x is 10, sigma x is the square root of 4, 2 milliampere. So we are replacing x with x minus mu x by sigma x. Probability of x less than or equal to 1. So probability of x less than or equal to 1. We know that the probability of x less than or equal to 1 is distribution function, which is equal to 1 minus q of x. So this is equal to 1 minus q of x. So this is equal to q of x. So q of 1 is approximately 0.1587. So there is 15% chance, 15.9% chance for a current to exceed 12 milliampere for a given normal distribution function. This is how we can apply the concept of q function. Let us take one more example. Here the lifetime of integrated circuit chips manufactured by semiconductor manufacturer is approximately normally distributed as 5 into 10 power 6 hours. The standard deviation is also 5 into 10 power 6 hours. A mainframe manufacturer requires at least 95% of batch should have lifetime greater than 4 into 10 power 6. So will the deal be made? So based on the given data, whether deal will happen or not. So see here, the mean value mu x is given as 5 into 10 power 6 and the standard deviation is given as 5 into 10 power 6. Now, a mainframe manufacturer want to purchase this IC chips and requires at least 95% of batch should have lifetime greater than lifetime. X indicates the, now random variable x indicates the lifetime of the IC chip. Lifetime should be greater than 4 into 10 power 6. Now what we will do is, first we will calculate z is equal to x minus mu x by sigma x. Every time we will replace x with x minus mu x by sigma x. We will make the Gaussian function into a normalized Gaussian function. From the normalized Gaussian function, we use the special function q function for calculation. So, x minus mu x by sigma x. So, calculating this, x minus mu x, 4 into 10 power 6 minus 5 into 10 power 6 by 5 into 10 power 6. So, we will get minus 1 by 5, minus 1 by 5, that is minus 0.2. So, the probability of x greater than given value 4 into 10 power 6 is mathematically equal to probability of z greater than minus 0.2. So, this can be written as 1 minus probability of z less than or equal to minus 0.2. This can be written as 1 minus f of minus 0.2. f of minus 0.2 is equal to 1 minus f of 0.2. So, that is f of 0.2. So, the q function of this value is 0.5793. We will get the 0.5793, 57.93%. So, but in order to deal should happen for a mainframe computer, the IC chip lifetime should exceed 4 into 10 power 6. This is the criteria they want. They need 95% chance so that the IC lifetime chip will be greater than 4 into 10 power 6, which is not possible here. Based on the deal requirement, the probability of estimation is giving for the given data is 57.93 chance. That means closely 58% chance is there. So, definitely the deal will be closed. So, this is one problem based on real time example. So, another problem related to the Gaussian random variable. A company conducts a test for job aspirants and passes them if they achieve a score of 500. So, if the score exceeds 500, they will pass the candidate or job aspirant. If the test scores are normally distributed with a mean value, average value as 485, deviation from the average value or standard deviation is 30. What percentage of the aspirants pass the test? So, totally x is given as 500 and mu x is given as 485, sigma x is given as 30. We need the probability x greater than 500, x greater than to achieve a score of 500. So, probability of z greater than x minus mu x by sigma x. X is 500, 500 minus 485 by 30, we will get probability of z greater than or equal to 1 by 2. That is probability of 1 minus probability of z less than 1 by 2. In terms of q function, 1 minus q of 1 by 2. So, we will get 0.3085, 30.85% of aspirants will pass the test based on the given data. So, let us see one more problem related to the Gaussian random variable. So, in a test there are 2000 electric bulbs. It was found that the lifetime of a particular make was normally distributed with an average life of 2040 hours and the standard duration is 60 hours. So, the average lifetime is 2040 hours for a bulb, electric bulb. The total number of bulbs are 2000 and the standard deviation is 60 hours. Now, they are asking us to calculate what is the probability that the number of bulbs likely to burn for more than 2150. Probability of x greater than 2150. This is can be written as probability of x greater than x minus mu x by sigma x. Applying this, substituting 2150 minus 2040 by 60, we will get probability of x greater than or equal to 1.833, that is z greater than. So, 1 minus p of z less than 1.833. This can be computed using the q function 1 minus phi of 1.833. So, the q function value gives you 0.9664. 1 minus this you will get 0.0336. That means the number of bulbs out of 2000 electric bulbs, the bulbs expected to burn more than 2150 hours is 67. So, only 67 bulbs will burn if expected to burn after 2150 hours of usage. Next one is less than 1950, less than 1950 hours. Again, we need to calculate the normalized random variable z is equal to x minus mu by sigma. We will get minus 1.5. The probability of x less than minus 1.5 is equal to q of minus 1.5. That is 1 minus q of 1.5. We will get the value 0.00668. So, the number of bulbs expected to burn less than 1950 hours is equal to 2000 into this value. We will get 134 bulbs. 134 bulbs may burn if the time is less than 1950. Similarly, if the time is lying between 1920 and 2160, what is the probability? Again, we need to calculate x minus mu x by sigma x. Calculating that, we will get the range is minus 2 less than z less than 2. That means phi of 2 minus phi of minus 2. We know that phi of minus 2 is equal to 1 minus phi of 2. So, we will get 2 into phi of 2 minus 1, 0.9544. Now, we will calculate. So, 1909 bulbs. The number of bulbs with lifetime between 1920 and 2160 hours is 1909. So many number of bulbs lifetime fall between 1920 hours and 2160 hours as per the given data. And this is more practical example. When an exam is conducted, let us say the average test marks in a class is 80, the deviation is 6. If the marks are distributed normally, how many students in a class of 200 receives marks between 70 and 90. So, 70 and 90, the probability of x lying between 70 and 90. So, what we need to do? We need to replace 70 minus mu x by standard deviation less than 70 minus 90 by 6. We will get probability of minus 1.67 less than x less than z less than 1.67. So, calculating this, we will get 2 into q of 1.67 minus 1. Substituting this value, we will get 0.905. Now, we need to estimate the number of students who receives marks between 70 to 90 marks for a class of 200 strength. Now, let us calculate for 200 strength, multiplying with the probability, we will get 181 students will receive the marks between 70 and 90. So, in today's session, what we have seen is, firstly, we have defined what is meant by a continuous random variable, and we have seen the definition of continuous random variable. We have seen the density function and distribution function of Gaussian random variable, and we have seen very few applications related to Gaussian random variable. And we have solved some real-time problems related to Gaussian random variable. So, in the next session, what we will see is, we will see the uniform random variable. Uniform random variable we will define, and we will see problems related to the uniform random variable. Thank you.